Welcome to The Explainer. Today, we're diving into one of the most exciting frontiers in artificial intelligence, something you probably interact with every single day without even realizing it: graph neural networks. So, think about these three things for a second. You've got social networks, the way proteins fold in our bodies, and the complex web of financial transactions. On the surface, right, they seem totally different: friendships, biology, money. But what if I told you they all share the exact same hidden structure? That's the secret. They are all networks, or what a computer scientist would call a graph. And for the first time, AI is actually learning to understand this kind of messy, interconnected data that, let's be honest, pretty much runs our world.
To really get how this new AI works, we first have to see just how much of our world is built on these structures. In so many ways, our world really is just one giant graph.
So what even is a graph? Well, it's actually super simple. You've got a bunch of dots, which we call nodes. Those can be anything: people, companies, atoms. And then you have lines connecting them, which we call edges. And those are the relationships, like friendships, transactions, or chemical bonds. That's it. Dots and lines.
Okay, so if these things are everywhere, why did it take AI so long to figure them out? Well, it turns out that their beautiful simplicity for our brains makes them an absolute nightmare for a traditional computer algorithm.
Here's the core issue. The AI models we're all familiar with, the ones that are amazing at recognizing images. They love order. They thrive on it. An image is just a perfect, predictable grid of pixels, right? Every pixel has a specific address. But a network? It's total chaos. There's no top left corner of your friend group. The way you draw it on paper is completely arbitrary. And this means you can't just feed a network into a standard AI like you would a picture. For one, the network could have 10 nodes or 10 billion. But the real kicker is that the order doesn't matter. It shouldn't make a difference if you list your friends alphabetically or by height. The network of your friends is still the same. And that simple idea, it completely breaks algorithms that expect everything to be in a nice, neat, predictable order. But here's the really clever part. The big breakthrough for understanding these chaotic networks, well, it actually came from borrowing an idea from the super orderly world of images. The big aha moment was this: what if we just think of an image as a very, very simple and well-behaved graph? I mean, think about it. Each pixel is a node, and it's connected by an edge to its immediate neighbors. That's it. And this little shift in perspective unlocks everything. If AI can already handle this simple grid-like graph, maybe we can use the same basic principles to teach it to understand any graph. You know, when an AI learns to see a cat in a photo, it doesn't look at the whole thing at once. It starts small. It zooms in on one pixel, and then it looks at the pixels directly touching it, its little neighborhood. By looking at the colors in that tiny patch, it starts to recognize a little feature, like the curve of an ear or the texture of fur. And that brings us to the million-dollar question. This whole neighborhood trick works great on a perfect grid, where every pixel has the same number of neighbors. But what about a messy, real-world social network, where one person might have 2 friends and another might have 2,000? How do you define a neighborhood then?
The answer is an idea that is so simple, it's brilliant. And it is the engine at the very heart of modern graph neural networks. It's called message passing. The idea is you forget trying to see the whole network all at once. Instead, you just give every single node in the network one simple job. Look at your direct neighbors, gather information from them, these are the messages, and use what you learn to update yourself. That's really all it is. Every node is just listening to its local gossip. A node representing you on social media might learn about the music your friends are listening to. An atom in a molecule learns about the chemical properties of the atoms it's literally bonded to. But here's where the magic happens. You run this process once, and every node knows about its immediate friends. What happens if you run it again? Well, now each node is getting an update from its neighbors who just got an update from their neighbors. So suddenly, your node is learning about its friends of friends. Do it a third time, and it's learning about friends of friends of friends. With every single step, the node's view of the entire network just expands outwards, layer by layer. This super simple process of just listening to your neighborhood is an absolute game changer. It gives AI a way to finally understand context and relationships, which unlocks solutions to problems we used to think were impossible to solve. And we're talking about massive, real-world impacts here. By understanding the graph of a molecule, GNNs can help discover new life-saving drugs.
By analyzing the network of financial transactions, they can spot those really complex fraud rings that no single human could ever see. And, of course, they power the recommendation engines that can predict who you might know or what you might want to buy next.
You know, the craziest thing is, we have only just begun to scratch the surface. GNNs give us this powerful new lens for looking at the world, a lens that finally sees the connections, not just the individual pieces. From the human brain to the cosmos itself, our world is built on networks. So the only real question is, with this amazing new tool, what will we understand next?